And first of all, I'd like to thank the organisers, in particular Eric, for the opportunity to participate in this workshop in this delightful setting here in Puerto Rico. And also, it's my first chance to catch up with Eric after he spent a sabbatical leave down under in Brisbane a few years ago. Well, this title I put together after a suggestion from Eric, but it's really an area in which I've been sort of working on. It's a topic I like. I'm not saying I've done anything profound in the area, but I like fiddling around with this topic. And so we're going to see the local false discovery rate is a key concept, I think, in multiple hypothesis testing. And of course, multiple hypothesis testing comes up in a lot of problems, but in particular with differential expression. And that's the context in which I'm going to be looking at it. So multiple hypothesis testing arises in many applications. The detection of differentially expressed genes, and that's what I'm going to be looking at. It should also arise in GWAS, genome-wide association studies. And of course, it can occur in other problems, such as you're trying to build a classifier from a huge number of variables, and you might look at each variable separately to see if it's got some signal that could be used, and so you've got optimal feature selection. So it's rather interesting that Benamini said that Tukey told him that not to spend too much time on multiple comparisons, as people weren't really interested in, the interest was waning in the topic. But anyway, of course, these days there's a lot of interest. So finding differentially expressed genes, well, I think as Raphael Izarari said yesterday, that this is a very common problem in bioinformatics. And we're trying to find genes that seem to be behaving differently in some different classes. And I'm just going to focus on two classes here today. And so why differentially expressed genes? Well, often it's the first step of a microarray study after the pre-processing and the normalization of the data. And it can be related to problems of trying to find marker genes in supervised classification. So if we've got some, say, expression arrays, say capital M, then we can summarize the data in the form of this matrix, n by m. So, each column here refers to the output from a single array, giving the expression levels on a large number of genes, capital N. And there's lots of problems in bioinformatics. One could be trying to cluster these genes, perhaps trying to see which genes are co-expressed. Or one could have some time course studies where this perhaps is the same tissue being observed at different points in time. Or one could be trying to cluster the columns and work out why people with similar clinical characteristics, some respond to chemotherapy and others don't. But today, or this morning, I'm looking at this problem where the samples have been dichotomized into two classes, and we want to see which genes seem to be behaving differently in these classes. Now, I must admit, when I first went into bioinformatics, I was a bit surprised at how much emphasis biologists placed on fold change. And in preparing this talk, I came across this letter to the editor by Lev Klebanov and colleagues. His colleagues are at the university. He himself is at Charles University in Prague, and his colleagues from University of Rochester, led by the late Andrei Yakovlev, who unfortunately died about 2.5 years ago. And what prompted him to write this letter was this sentence in these two papers. Now, yesterday Terry mentioned the MAQC2, the Microarray Quality Control Project 2. This is the results of the what would now be the MAQC1. So this was a project that was looking at the reproducibility of inter-platform, inter-laboratory microarray data, and there was a follow-up paper. It comes immediately after this paper, where they were looking at further validation and extensions of the results in this paper. And so they make the statement that they do qualify it by saying that they want the genes also to achieve a modest level of statistical significance, but it seems to be coming out that sort of in favour of fold change. So I was surprised to actually read these two sentences, and but I didn't have time to follow it up to see what the reaction has been since then. Of course, the reason why they actually did have a reply to his well, first of all, he stated that fold change is ignoring the error, so you can get into trouble. And the thing is, they placed a lot of emphasis on the stability of the class of genes they got in these site cross comparison things. But of course, if you've got a method that's performing badly, you could have a method that's performing, giving constant results, but they could be bad results. And so the emphasis just on stability as a criterion is perhaps it is a bit worrying. So you can actually perform a simulation experiment to show that fold change can give you misleading results. And this is what Klebanov et al. Did. I'll come back to that slide. So what they did was to generate, to generate 800 genes. First of all, these genes are null genes, not doing anything. This lot here, you can see they're going to cause problems in the sense that this variance here is so much greater than that. So they're going to get a lot of false positives if they use fold change. These genes here are behaving I suppose like in a typical fashion after normalization for differentially expressed genes. They got a Mahalanobis distance of 2, but these here, the distance between the means has been reduced down considerably in Euclidean distance, but they've made the variance very small, so the Mahalanobis distance is the same. But of course, if you use fold change, you're going to probably miss a lot of those genes. So you can see this experiment has been designed to make sure fold change doesn't work, I suppose. And I mean, I don't do a lot of work at the coalface with microarrays, but I'm not too sure how realistic these things would be if after normalization you'd expect genes to have such different variances in the classes. But so coming back to their result, they had 5 tissues in each class and then 15. And then they decided, okay, let's rank the genes according to the fold difference and the t statistic and pick out the top 100 or pick out the top 150 and so on. And they did this a number of times, and then they reported the mean results with the standard deviations. And if you look down here quickly at the power and the false discovery rate, you can see that the fold change is not doing very well. Anyway, that's enough. So I think, well, most statisticians would agree that we need to take into account the error of the standard error of the difference. And so this particular data set, the head and fork breast cancer set, has been analysed perhaps to death in the literature. There are 15 patients, and 7 women have the BRCA1 mutation and 8 the BRCA2, and there's 3,000 odd genes left after the pre-filtering. And the problem is to find which genes are differentially expressed between the two classes. And this is just like a first-year problem in statistics, so that we've got some gene here, and these are the values after the normalization. We work out the sample means and sample variances. We may pool the sample variances. We get a value for the t statistic, and then we can work out the p-value, which here is 0.5. Now, if one's worried about using the t statistic for small sample sizes or things like that, we can actually do a permutation test where you just permute the class labels. And if you do it just for the particular gene, if you've got small sample sizes, then you can run into problems because the distribution is too granular. And so you're forced to pool across the genes. And of course, all the genes aren't null, and so you'll get a conservative estimate. But it seems to do reasonably well in practice. So that I'm assuming now that we've got a p-value by some method. And And now we want to proceed. We want to control the false discovery rate, or in particular the local false discovery rate. So we've got this multiplicity problem. We know that we're going to get a lot of false positives. How do we deal with this? Well, we've got the Bonferroni method, and I think I recall Terry Speed saying the Bonferroni method, part of the popularity is due to the catchy name that it's got. But obviously that becomes too strict if you've got a lot of genes. And so the idea, of course, is to use the false discovery rate to try and control that. Okay, so if we look at these, what's going on here, this computer's done something to my subscript. Here it's, oops, it's taken my R subscript down here. Anyway, well, the false discovery rate, or the empirical false discovery rate, is the number of false positives over the number of genes that are declared to be significant, the number of rejected hypotheses. And, but also of interest is some other error, the type you can make. Well, the false non-discovery rate perhaps is not of interest because generally you've got a large number of genes. So this is always going to be small, and it probably makes more sense to look at the false negative rate, which is given by this. And, of course, the false discovery rate, the actual definition, is the expectation of this ratio, where this denominator is defined to be 1 if there's no rejected genes, and similarly for the false non-discovery rate. Now, so I want to just talk about the local false discovery rate, and as Ephron says, that this model perhaps is too simple to try and say one person first suggested it, but basically I think Mai Ling Ting Lee, Brad Ephron and Michael Newton were among the first to propose this two-component mixture model. And so I've been working with mixture models for many years now, and so when I saw this I took additional interest in what was going on. And so you've got a test statistic associated with the Jth gene, and I'm going to convert my test statistic to, I suppose everyone here would say z-scores. I say z-scores. I'll try and say z-scores, but if I lapse into z's, you know what I'm talking about. So we've got a test statistic associated with the Jth gene, and then we're going to actually convert it into a z-score. So that's why I've written the z here. And now we say there's a proportion of genes that are not differentially expressed, null genes, and they have a density, and then 1 minus pi naught is the proportion of genes that are differentially expressed. And so the local false discovery rate is given by this notation here, tau sub naught zj. So it's the probability that the Jth gene is null given that you've observed the value of this test statistic. And if you use Bayes' theorem, it's simply given by the proportion of null genes times the density under the null density, and then you just got this mixture density on the denominator. So I suppose you can think of this as arising in an empirical Bayes framework, but of course we're not. Well, I'm not using this in a Bayesian framework. I'm not going further and putting priors on these parameters here, but of course you could do that. And this is a very simple example taken from a paper that actually I think Terry Speed gave. It was published in the Spanish magazine Test. And two Australians, Gary Glonick and Paddy Solomon, gave this in the discussion. So suppose that your test statistic is a normal 0.1, and then under the null, and then has this distribution, normal 1,1, under the alternative, and the proportion of null genes is 90%. And so the proportion of differentially expressed genes is 10%. And suppose you're going to reject the null hypothesis if the test statistic is greater than or equal to 2. Now, if you work out, so here's the two densities weighted by their weighted by their prior probabilities. Tau sub 0.2, this is the local false discovery rate. So you can be pretty confident that a gene with the value 2 is not differentially expressed. But the false discovery rate, which is concerned about the proportion of the genes that are differentially expressed, is 0.17. Oh, I'm sorry, the ones which are wrong. the false positive, I should say. Now, if you change this 0.9 here to 0.6, the two densities now change because you've got those, they're weighted by the prior probabilities. And so now if you get a gene that's got a value of 2 for the test statistic, you're only 25%. The, if you like, posterior probability that it's not differentially expressed falls to 25%. But the false discovery rate is the same. So the false discovery rate is sort of making a global statement about what's going on, the number of false positives, whereas this is about a particular gene. So, as I was saying, the global false discovery rate is concerned with the average number of false positives among the selected genes, but the local FDR gives a probabilistic assessment of differential expression for each gene. And if you use mixture models, you can give estimates for the local FDR as well as the global FDR and the other error rates like the false negative rate. And well, basically Efron goes on from here now to use a non-parametric approach to estimate the local false discovery rate. And he has to make some assumptions. So he makes the assumption that the proportion of null genes is very close to 1. But as I say, I've been sort of fooling around with mixture models for ages. So I thought I would try and fit these mixture models in a parametric framework. Oh, the other thing about using a local false discovery rate is that, or a mixture model approach, is that you can use this concept introduced by Efron of an empirical null. So here we have the local false discovery rate again for a particular gene, the J gene, where it's got this value for its test statistic or for its z-score after conversion. And we want to try and estimate this quantity. So suppose we do estimate it, and we're going to declare genes to be differentially expressed if the estimate of it is sufficiently small. So we choose some constant C0. Now, just suppose that it's a monotonic decreasing function in Z, so if it's less than this threshold for Z sub j greater than that, then we can actually write down, get an estimate of the false discovery rate by this. And you can see that if you take the expectation of this quantity here, it equals this if you forget these estimates. Of course, this is true in general, but I'm just assuming this to show that you can work it out under this assumption. But this holds in general. So if you get an estimate of the false discovery rate, the global false discovery rate, then if you choose Z sub naught to be the argument of Z that minimises this, then essentially you're doing what Benamini-Hochberg does if you take pi naught hat to be 1 and take this estimated distribution function to be the empirical distribution function. So what we're effectively doing is putting in an estimate for pi naught rather than taking it to be 1, and instead of using the empirical distribution function, we're estimating the mixture distribution function parametrically rather than by the empirical distribution function. So we've got this p-value, and of course, if we think the p-value has been calculated correctly or the assumptions are correct, it'll have a uniform distribution, so it's got a beta 1,1 distribution, and this led Allison to say, okay, well, we're going to fit mixtures of betas. And so he fits the mixture model. The first component is a uniform, so that handles the genes that are null genes, because the p-value would be uniform, a beta 1,1. And then he fits an additional beta to handle the alternative, the genes that are differentially expressed. He also fits 2 betas, but there's very little difference. But fitting mixtures on the interval 0,1 is not as nice as using the whole real line. And so what we do is we want to work on the whole real line. So given a p-value, we convert it by using basically the Probit transformation. So we can convert our p-values to z-scores. And this is the distribution function for the standard normal. So if this p-value is going to have a uniform distribution under the null, then this will have a standard normal. And for genes that are differentially expressed, they're going to show up by having large positive values for this z-score. So we're back on the whole real line, and we can fit normal mixtures. So we can rank the genes according to their z-scores, which should be the same as the p-values. And then if we can get an estimate for this, if we can get an estimate for this local false discovery rate, then we can declare a gene to be differentially expressed if the estimate falls below some threshold C0. Now, if we do this, we can tie this in with the Bayes risk. If we do this, the risk is given by 1 minus the value of the threshold times pi naught, and this E naught 1, this is the probability of a false positive, and then we get C naught times pi 1, which is 1 minus pi naught, times the probability of a false negative. So this threshold here, it's just has this impact in what weight we're putting on these to the two errors we can make. And you read papers these days that come out, in particular in the bioinformatics literature, where people derive these results. But if you go back and look in Lehman's original book on hypothesis testing, he does have this link with this. With the Bayes risk. So I've taken this from a paper from Efron. So if we're going to reject a gene if its local false discovery rate is less than C, how does that stand up to what we would do in a standard test when we're looking at one gene at a time? So if you run through the algebra here and suppose that pi naught over 1 minus pi naught is less than 9, basically we're saying that a gene, to be differentially expressed, its density under the alternative divided by its null density has got to be greater than or equal to 36. So that's basically what we require, if this is the case, for a gene to be differentially expressed. Now what happens in a standard, so that's to summarise that result there, where for genes to be differentially expressed, if you like, the likelihood ratio has got to be greater than or equal to 36. Now, in a standard test where you're just looking at a single gene at a time, so suppose the alternative says that mu equals 2.8, right, and the null is 0, then if you reject the null using a test of two-sided test of size 0.05, and the power it comes out to be 0.8 for this particular thing, then the likelihood ratio is 4.8. So in just testing one gene, you basically the likelihood ratio has got to be greater than 4.8. But of course, in the context of this multiple hypothesis testing, we're taking it to be it's got to be greater than or equal to 36. So that gives you some idea of how stringent the additional condition required to make a significant result when you're doing multiple hypothesis testing. So back to this local false discovery rate, we have to estimate it now, and so for the moment anyway, we're assuming that this has got a standard normal distribution. We're assuming that the p-value has been calculated under correct assumptions, and it'll have a uniform distribution under the null. So that means the z-score is a normal 0.1. Now we've got to try. Now we can easily estimate this, the mixture density, but in order to estimate the proportion of genes that are the null genes, we've got to make some assumption about pi 1, the density of the z-score for the differentially expressed genes. And we can do that by just specifying to have a normal distribution. So we've got to estimate pi naught, and we've got to estimate mu1 and sigma 1 squared. Now, if all the differentially expressed genes had the same effect, then this assumption is a good assumption. If you work out what the distribution is, and Efron has done some analytical calculations to show that this is basically, if you ignore terms of order, 1 on n to the 3 on 2, I think, then this is a normal mu1 sigma 1 squared. But that's if all the genes were the same size. And of course, we might have genes where some are only slightly differentially expressed, others moderately and highly. But it seems in the data sets we've looked at, we can get away with just fitting one normal distribution. Of course, you can look at the fit, and if the fit seems that you need an additional component, then you can fit an extra normal component. But now, so how do we fit this? Well, this is this can be easily done. So, these are just some simulations. If you don't believe that the alternative distribution is behaving like a normal, then for effect sizes of 1, 2, and 3, you can see that it's basically a normal. Now, we've got this program, MMix, which stands for EM-based mixture analysis. We call this MMix FDR. It's a program we've got for fitting this this normal mixture model to the z-scores, and it's very easy to fit because once you specify pi naught, the proportion of null genes, the maximum likelihood estimates of mu1 and sigma 1 squared are obtained, so that so basically. You've used the EM algorithm and you have to give the parameters some initial starting values. Well, the null density, it's fixed. It's got a mean 0 and a variance 1 that are fixed. But once we give a value of pi naught, then the values of mu1 and sigma 1 squared follow. So we've really only got the 1, 3 parameter. And so you can just run this EM algorithm from different choices of pi naught. Or you can start with, generally pi naught is a fairly high value, and then you can just start the thing running from values of pi naught. Now, if you don't want to spend time running the algorithm for all values of pi naught greater than some value, then you can use this particular starting value here. You can just solve this equation. So n sub xi is just a number of genes to the left of xi. Number of genes whose z-score is less than xi. And then this n pi naught is the expected number of null genes, and this is just the area to the left of xi under the standard normal. So the only unknown quantity in this equation is this mixing proportion, and that gives you a ballpark figure for pi naught. Or you can take pi naught to be given by this expression here, where J star is the argument that maximizes this particular quantity. Now, this result is taken from a paper by David Donahoe and colleague in PNAS in 2008. They weren't interested in finding genes that differentially expressed. They were fitting a classifier from a large number of variables, and they were looking at each variable separately to see which variables could be selected. So anyway, if you want to sort of get some idea what pi naught is before you start, then that's two possible ideas, but not the only, two possible suggestions, but not the only ones. So here's for the head and fork data set that I mentioned earlier, here's our distribution, our histogram, I should say, for the z-scores, and we're fitting a mixture of two normals to it. So the green curve is the standard normal weighted by pi naught, the estimate of pi naught, and the red curve, remember we're only just using one single normal to handle the non-differentially expressed genes, and it's weighted by 1 minus pi naught, and this is the overall fit that we get. And if we're unhappy with the fit, then we could fit an extra normal or two. Or we could, if we had genes out here, we could truncate them and then fit mixtures of truncated normals. But and now, once we've fitted those mixture models, we can find these estimates of the false discovery rate. So, so this notation looks probably a bit involved for this time of the morning, but this is the indicator function, and it's 1 if the argument falls in this interval. So to get an estimate of the false discovery rate, we just sum over all genes. We put in the estimate of the false discovery rate here, and we count that particular gene if its estimated local false discovery rate falls in that interval. And then we divide by the number of genes declared to be differentially expressed. And similarly, we can estimate the false positive rate, the false non-discovery rate, and the false negative rate. So once we've got an estimate of the local false discovery rate, we can get these other estimates. And it's important to have some idea what the power is going to be, because this essentially is 1 minus the power. So, and for example, with the head and fork data, suppose we were going to declare, so these are the genes, and suppose we rank the genes in increasing order of the local false discovery rate, we might decide, okay, we're going to draw a line and declare all genes with an estimated local false discovery rate less than 0.1 to be differentially expressed. And these values are the values for the head and fork data. And so if we add up these estimates here and divide by 143, we get an estimate of the false discovery rate. It's roughly 6%. But, I mean, there's no reason why we want the false discovery rate to be around 5%. There's no sort of universal level for that. But so basically, it gives us some idea what's going on. Now, we might think, what would happen if we went down to 200? And, well, if we add up these estimates here and divide by 57, because we've got an additional 57 genes, take it away from 1, then it's saying that there's 89%, well, that's the estimate. We estimate that there's 89% false negatives here. So there's a lot of genes that we're not... If we're going to draw the line here, then we're going to ignore a lot of genes that could be positive. But so it's up to, I suppose, what the biologist wants to do, how much time they want to spend in looking at these genes, whether they want to go away. And because the other thing is, of course, it's not necessarily the genes that have got big differences are the ones that the biologists are trying to find. Sometimes the effect is quite subtle, and they actually want to go down the list. Now, you can vary the threshold. It gives you how many genes declared differentially expressed, what the false discovery rate is, and then the false negative rate. So if you're willing to entertain a higher false discovery rate by taking the threshold to be 1/2, then the false negative rate drops to 37. But you've got 971 genes declared differentially expressed, and so that's a large number. So, but I suppose the biologists can choose to how many genes they want to, or whether their favourite gene is among these genes here, and perhaps it's down here, sort of. So, as a matter of interest, this data set I said has been analysed by many people in the literature. These are just some estimates of pi naught that have been produced, we've got an estimate of 0.65 when we use a theoretical null. Now, Efron suggested that because we've got a lot of genes, and the bulk of these genes are null genes, then we can try and use that information to estimate the null distribution when we have some doubts about the assumptions. So these points are taken from a talk that Brad Efron gave at a JSM meeting about 2 years ago now. So where would it have been? But anyway, perhaps in Seattle. So first of all, the theoretical null may not hold for 4 reasons. And one is non-normality distorts the T distribution. But as I mentioned, we can use permutation method, so that's not a problem. The other problem is there's correlation across the rays. And the student T density, taking the null density to be the student T assumes independent. And permutation methods can't help then. And the other thing is that you've got these unobserved covariates, like age, weight, and stage, which tend to widen the null density. And the fourth reason is, of course, the genes may be correlated. And so you can estimate the mixture density okay, but you could run into trouble trying to estimate the numerator there. So if we assume that the genes are independent for the moment, and just look at how we handle 1, 2, and 3, the Efron's suggestion is that, okay, we just estimate pi naught from the data. And so we do that by, we're now going to take this, instead of taking this to be a normal 0.1, we're going to take it to be a normal with a mean and a variance we're going to estimate from the data. So this seems great, sort of, in a way, but and for a lot of data sets, it works okay, but some particular data sets, there's not enough information in the data set, because you've got this concept of, well, you've got the identifiability problem. The mixture model is identifiable, but you run into what's called so-called practical identifiability. That is, a sample size has to be really large to be able to identify these two components, because you can get two solutions. That is, I can get one solution with a value of pi naught and these parameters, and I can get another solution for a different value of pi naught and different values here. So to make a choice between those two solutions, which are giving essentially the same mixture density, you need either some additional information, like you think pi naught should be close to 1 or something like that. But of course, if you get a data set that's causing these things, well, I suppose you just declare it to be a data set where there's just not enough information to allow you to make these inferences, and you perhaps go away to look at taking more observations or something like that, more arrays. So we can easily fit this, if you like, empirical null. There's no problems in fitting it, as I say, but you can do a test whether you need the empirical over the theoretical, and so everything seems fine that way. But as I say, it can make a big difference whether you use an empirical or a theoretical. You can look at the fits given by the theoretical null and the empirical null. There's not much difference to the eye, but it can lead to quite a difference in the number of genes being declared differentially expressed. Now, the fourth reason, okay, so we know that not all the genes are independently distributed, and so by using an empirical null, we can try to look at this. Because at the point that Efron makes is, even though for a given gene the p-value may be behaving like a uniform distribution, may have a uniform distribution for a null gene, when you look at the ensemble of the p-values, or the z-scores, they're not behaving like a sample from a standard normal. They're not behaving like a random sample taken from a normal distribution. So each gene, the z-score may have a normal 0.1 distribution, but when you look at the ensemble of them, the collection of them, they're not behaving like a random sample from a normal 0.1 distribution. And so, but we can still do that. And now the thing we're using the likelihood now is the maximum. The likelihood is not the true likelihood anymore, but we can justify this use because, you know, as the sample size becomes large and you use maximum likelihood, you're really choosing that member of the proposed family that minimises a Kullback Leibel distance between the true density and a member of the proposed family. So we can do that. And so here we have the head and fork data. Again, we've got, this is our mixture density with a theoretical null. That's a standard normal 0.1 weighted by pi naught. And this is 1 minus pi naught weighting the alternative density. And then we've got the empirical null, where we actually estimate the null distribution. So this is the table I had up before when we had a theoretical null. This is what you get now if you use an empirical null. Well, it's a bit hard to retain those two tables. So let us just look at what happens for these two threshold values, 0.1 and 0.2. So if we use a theoretical null, we get 143 genes being declared differentially expressed. If we use an empirical null, we only get 62. And if we use the threshold to be 0.2, we get 338 genes being declared differentially expressed.
with a theoretical, and with an empirical one we get 212. So although the fitted mixture densities there's not much difference between the theoretical and the empirical null solutions, it does make a difference in the number of genes being declared differentially expressed. Now, we can do some simulations, and of course it's very difficult to try to work out what's going on in a real data set with genes being differentially expressed. But what people have tended to do, and this is what Alison did, is to say, okay, the genes are going to be sort of correlated in blocks, and time's moving on, so I won't describe the simulation too much. But basically, we're generating these gene profiles now to have some correlation, and now what would happen if we ignore the correlation and use a theoretical null? Then this is our fitted mixture density here. So this is a theoretical null because we force this density to be a normal 0.1, and that's the overall fit. And if we allow the null density to be estimated, then this is our estimate. The mean is minus 0.24, and the variance is 0.93, and we get a better fit. And if we look at those on the same curve, then you can see the red is using the theoretical null, and the empirical null is given by if we use an empirical null, then we get this black fitted mixture. And I'll skip through the other curves which show roughly that thing. But of course, in a case of a simulation experiment, everything looks fine. But as for a real data set, we don't really know how the correlated genes are behaving. So, the main reference and what I've been talking about is this paper here in Bioinformatics, published in 2006. As I said, I've been looking at this problem for a long time. Our main aim is to try to get a program that's very user-friendly for biologists, but we keep looking at data sets and coming up with data sets that have some peculiar characteristics, and it always makes us think, now how can we handle that situation so that the biologist is not too upset by getting that result? And as you know, the literature on this topic is huge, but I've just put up some of the papers that Efron has written on this particular topic. As you know, I've got a joint appointment in the Institute for Molecular Bioscience, and biologists do say to me from time to time, why are you still fiddling around with this particular problem? You know, you've got a t-test, and what keeps your interest so much in this particular problem? And then I say to them, well, look at these papers written by Efron, sort of, that, well, they don't know who he is, but I tell them that he got the medal, the National Medal of Science from the President of America, etc. But anyway, and here are a few other ones by Michael Newton on this and others on this topic. Now the summary, well, this mixture model approach defining differentially expressed genes is both convenient and effective. It gives a measure of the local false discovery rate as well as the global, and you can use an empirical null if you think the theoretical null may be misleading. Future research, well, I brushed over how we might, if we're going to use the t-test, how we might want to get a good estimate for the sample variance, because that's crucial. And some recent papers on this. So what we'd like to do is just cluster the gene profiles and then pick out the clusters that correspond to the null genes. And we don't have to worry about p-values and things like that. And so this paper in the Annals of Statistics by Russell is one of the latest ones. And there are two parameters in the gamma this uses a gamma distribution for one parameter and a gamma for the other. So the Gaga reminds me of, is it Lady Gaga or something? But and then this one is me Gaga. So it's got a mixture of gammas for one parameter and a gamma for the others. So this is like an extension of the work done by Michael Newton and Christina Kinziorski, where they do clustering. And of course, Gordon Smythe's got this lemma, but it's using a moderated T. Now, so we've got this program that came out in Bioinformatics in 2006 called MXWire. So
the Y here stands for with random effects. So this is a little bit like the model that I think Terry put up, or similar, like a mixed model. We've got these fixed effects here, so these two terms would be the same if the gene was not differentially expressed. These values would be the same. This is to allow for the arrays to be correlated. And Efron did find that some of these arrays for the head and fork data did seem to be correlated for some reason. And then this random effect term here is some attempt to allow genes to be correlated. So this term here means that if genes fall in the same cluster, they share this random effects term here, and they are correlated. And this term makes the fitting of this mixture model very difficult. We can easily handle this term here because the correlated observations are on the same gene base. But when they're on different genes, you can't write down the likelihood with this term here. And, can't write it down in a closed form. So, but we got the EM algorithm, of course, and we can write down a complete data log likelihood. And so we sort of, away we go. And we can fit this thing. So, so what we did with this one was to just cluster the genes and then identify the clusters where these two terms look to be the same. And then those clusters, we say, OK, contain the null genes. And that gives nice results on some data sets. But the problem is, of course, it's a little bit ad hoc. If you've got a lot of clusters and you're trying to work out whether these things are equal or not, so it gets a little bit hand-waving, a little bit subjective. And it doesn't always... The trouble is it's very hard to get pure clusters when you cluster these gene profiles. And so have other authors found this using these Bayesian hierarchical mixture models. And what they've done is after they've done their clustering, they've decided to fit a mixture of 3 clusters to each of the clusters they get. One cluster is a null, one's to upregulated genes, another to downregulated genes when they've got 2 clusters. So what basically we do now, we use this model to cluster the genes, and then within each of these clusters we form, if you like, a modified t-statistic. And that modified t-statistic, its variance is being based on the estimates of the variance we get for each of those gene profiles in a cluster. And it seems to be working very well, but a student of mine will be speaking on that in Vancouver at the joint statistical meetings in August. But unfortunately, we didn't get the results finished to appear here. So I think basically that's the end of my slides. Oh, this is just saying that once you condition on this random effect C, you can write things down. But that's it. So thank you.